Excellent talk. Um, our next talk will come from Matt Barker from King's College London, who will be talking about translating latent state world model plans into natural language.
Thanks. Can everyone hear me okay? Perfect. Let's just try the clicker. Perfect. Yeah, hi everyone. I'm Matt, a PhD student at KCL. I'm going to be chatting through some work that I've done along with my supervisor, Matteo. So as some of you may know, latent state world models, that is world models that learn their own compressed representation about the world, have enjoyed a lot of success in recent years across a variety of domains, such as solving complex video games to being applied to real-world robotics. But the model of the world that these agents learn is unintelligible to us humans due to the black box nature of the deep neural networks they're trained with. So if we imagine sort of an agent in a kitchen environment, so sort of a robotic simulator agent, typically these world models take in this observation that the agent gets, encodes that into the model's own internal representation, which is essentially just a big vector of numbers that contains all the information that the model sort of has learned about the world. So this is the state of the world according to this model. But to us, this big vector of numbers is essentially just a black box, right? We have no idea what this actually means in terms of what the agent has learned to represent. So let's give this a symbol, S hat, since it aims to approximate the true state of the world, S. And these models afford the ability of the agent to plan in this latent state space. So an agent can imagine if I take some action A, this will change the world, which will lead me to a new state, S hat, which again is just another black box sort of vector of numbers. And this process can be repeated sort of an arbitrary number of times to yield what I'll call a latent state plan. But fundamentally, this plan and agents using this are unable to answer the simple but important question of what are you planning on doing? Since what we get out of the plan is essentially just a sequence of black boxes that mean nothing to us. And this poses some challenges for the real world. You can imagine, again, if we extend this sort of kitchen agent example, it makes this latent state plan and then it executes it in the real world. And we get something like this, where the agent is just picking up a whole bunch of objects and just throwing them around your kitchen. And there are obviously a whole bunch of other real world scenarios you can think about where we want to know what an agent plans to do before it acts in the world. So what would we like instead? Well, clearly agents that learn their own and models that learn their own sort of latent representation have been shown to be good. So I propose that we would like to keep that sort of efficient learning mechanism. But we want some ability to be able to translate this sort of black box representation such that the agent can verbalize what it plans to do before it acts in the world. So for example, this agent could state that it's just going to pick up and throw a bunch of objects in your kitchen. And then you might want to turn it off so it doesn't actually do that. So our work aims to address this. So we introduce what we call soliloquy, which means sleep talking, which is a bit of a playful nod to the fact that planning in these latent world models is commonly referred to as dreaming in the field. And we show that our method enables the following. So one, the agent can make a plan in this latent state space using some learned latent world model and a learned policy. And two, we introduce an encoder-decoder transformer to basically translate from this latent plan sequence into a natural language description that captures what the agent expects to do and perceive in the world. And then finally, we show that this enables the agent to verbalize their plan prior to acting into the world, such that what the agent says it will do is what it actually does do. So before we get into how we actually sort of train and do this thing, just a couple of quick bits of background. So we use the Dreamer v3 sort of state-of-the-art latent world model as our sort of method for learning this world representation. I won't go into too much details about this, but a very simplistic sort of overview is that Dreamer learns its own latent representation in sort of an autoencoder-like manner. So it sort of takes in observations, compresses that into some latent state vector, and then that learned representation is shaped to be useful in predicting the reward the agent may get in the state, reconstructing the input observation, along with predicting whether the current state is a terminal state or not. So i.e. has the goal been reached or has some sort of game over state been reached. And finally, there's another component that aims to mimic this latent representation, but without access to the observation. So you can think of this as sort of like the prior, and the one that gets access to the observation as the posterior. And it's this sort of prior component that allows planning in the world model, because obviously when you're imagining what may happen if you take some actions, you don't have the sort of ground truth observation that you would get in that sequence. And this whole thing is parameterized and trained via a collection of sort of deep neural networks. Hence, all these representations are just unintelligible. The other key bit of background is sort of transformers framed in the context of machine translation. So since the rise of transformers, sort of encoder-decoder transformers have been used to solve sort of machine translation tasks that involve going from some source language, for example, French, into some target language, for example, English. So to give a very brief summary, the encoder block basically takes in a sequence of tokens, or you can just think of it as words, in the source language, encodes that to a sequence of fixed length vectors that's passed over to the decoder block, which then is just trained to auto-regressively generate the translation. So at first it takes in, a special sort of beginning of sentence or sequence token, predicts the next word, that's then appended to the input to generate the next token, and this process repeats until the translation is complete. So on to how we model this translation in our context. So essentially, the key idea is rather simple. Instead of using transformers to go from, say, English to French, we use them to go from the language of latent state to English. So the encoder block now takes in a sequence of latent states output by Dreamer, and the decoder block is tasked with sort of auto-regressively generating the translation of what these states sort of mean in terms of the agent's interaction with the world. Now, this is trained in a supervised manner, so obviously a natural question is, where do we get the ground truth translations of these states? As by their nature, they're sort of a black box latent representations, and if we knew what they meant, we wouldn't need to do this whole thing, basically. So what do? So note that the latent states aim to approximate the true state of the world. So if we extend sort of the kitchen example, the true state of the world is basically all the information about the agent and about the kitchen, which would be relatively easy to take in and generate a description of what's happening in the sequence. But assuming that we have access to all this information is quite a strong assumption to make, even during training. So instead, what we do is we assume that just during training, we have access to a subset of this true state information. So for example, we might know where the agent is in the scene, we might know where objects are in the scene, and we might be able to tell which objects the agent has interacted with in the scene. So we assume that we have access to this just during training. I should note that each environment will have a sort of different set of these states, depending on sort of the states afforded to you by the simulator or environment of choice. So we then assume that there is some narrator object or function that takes in this sort of subset of true states. For example, this sort of, I'm not sure if you can see it clearly, but this is sort of a JSON-like representation of the agent's position and object interactions. And then the narrator is just tasked with outputting a description of what's happening in these states. So for example, in this sequence, it may output, I will start near the stove and I won't move much. First, I will pick up a pan. And we're agnostic to where this narrator comes from. So it could be human annotated data, it could be LLM generated, or as in our work, it could just be a sort of programmatic sort of Python function that basically takes as input those states and spits out a sort of description of what's happening. So in our experiments, we make sort of one of these narrators for each sort of environment that we test on. But crucially, we only need this during training. At test time and evaluation time, you can sort of discard all of this and just use the pre-trained sort of transformer to go from latent states to language. So now we basically have all the methods and components we need to actually train this thing end to end. So we assume that we have some data set that's populated as the agent explores, or in sort of more RL terms, this is your classic sort of replay buffer. And we're allowed to sample sequences from this. That gives us sequences of X's, which I just define as everything needed to train the world model, so everything needs to train Dreamer. So each X is just a tuple of reward, observation, continuation, and actions. And each sort of S tilde is that sort of special subset of states that we need to pass to our narrator. So then we can take these samples of sequences, pass in everything needed to train the world model, goes into the world model, which spits out its latent representation of this input sequence. And then the world model is updated in the sort of defined way. So this top line is basically just a very, very brief summary of Dreamer's world model training. And I should note that we do our thing in tandem with this. So we simultaneously learn the latent representations and how to translate those latent representations. We then pass these S tildes into the narrator to get the description of what's happening in the scene. So we get a sequence of tokens L, which are really just like a sentence describing what's happened in the sequence. We then can take this latent state sequence, pass it to our encoder-decoder transformer. This also regressively generates the sort of prediction of the translation. That's compared to the ground truth. We compute the cross-entry loss, and then update the transformer parameters in a supervised manner. Now, optionally, we can also allow this cross-entry loss to flow back through the transformer into the world model itself. So in other words, we can have the representations learned by the world model have an additional signal that they should be translatable. Now, in work that we've done post this sort of abstract submission, we found that this actually didn't have much performance in terms of the translation, but it actually slightly hindered task performance. So yeah, we need to do a bit more work in figuring out sort of what's going on there. Okay, so how do we evaluate our method? So we need to quickly distinguish between deterministic environments where there's no randomness and stochastic environments in which there is randomness. So in deterministic environments, what we really want to happen is this question, the answer to this question to be yes. So is what the agent says it will do what it actually does? So we can very simply evaluate this in a way that the agent makes a latent state plan. We translate that into natural language. The agent then executes its plan in the environment. The narrator gives us a description of what actually happened, and we compare the translation with the actual description. The more similar they are, the better our thing performs. In stochastic environments, it's a bit trickier because if you imagine, I don't know, an agent flipping a coin, a valid sort of plan and a valid translation of that plan is I'll flip the coin and it lands on heads. But then due to the stochastic nature of these environments, if you actually execute that plan in the environment and flip the coin, it may well land on tails, right? Which would be different to what you said would happen. So instead, we would like what the agent says might happen to be a sort of reasonable estimate of what may actually happen. And that's sort of vague. So what do I mean by that? Well, in the coin flip, if we extend that example, you would hope that 50% of plans and their translations would say it will land on heads, and 50% say it will land on tails. You don't want like 100% to always just like say, I'll flip a coin and it'll land on heads, or vice versa for tails. So we evaluate across 3 environments, one of which, the middle one, is new. So you won't find that in the abstract submission, but we've done some experiments on that since. So the 2 that are in our sort of abstract submission are Crafter, which is essentially like a 2D version of Minecraft. So the agent's rewarded for like harvesting resources, surviving, crafting objects, etc., etc. The environment on the right is our own sort of stochastic mini-grid environment in which the agent at the bottom left needs to get to the goal at the top right. But to get there, it needs to go through, step through some like teleporter objects. So each colored circle, essentially, as soon as the agent steps on that, it's randomly teleported to one of the gray circles, therefore inducing some randomness. And then finally, in the example in the middle, this is a robotic simulator environment in which the agent's situated in a kitchen. And we define our own sort of task where the agent is rewarded every time it picks up a unique object for the first time in the scene, which is why the policy you saw earlier is just results in the agent picking up and chucking things everywhere. Okay, on to some results. So yeah, these are updated since our abstract, but this is a measure of our sort of translation performance. So on the y-axis, this is essentially a measure of is what the agent says it will do what it actually does, where a value of 1 means like 100% yes, and a value of 0 is like completely not. And as you can see across 2 environments, we sort of converge to relatively high levels of similarity. In other words, what the agent says it will do corresponds very closely to what it actually does. And perhaps if people want to discuss the variations between environments, we can chat afterwards. So this is good. And we also have some examples. So we can compute a latent plan compute its translation, which is shown on the left, in which the agent states, like, it will first pick up a pan, for instance. Then we can get the observations from executing that plan, and you'll see at time step 3, right, the first thing the agent does is indeed pick up a pan. So that's all good. What I think is more interesting is cases where what the agent says it will do is not what it actually does in these environments. So this is basically an example where the agent sort of, for some reason, states it will just repeatedly pick up and throw a statue object in the scene. But when the plan is executed, it just throws the statue once and nothing else happens. But interestingly, so as an aside, Dreamer affords us the ability to decode the latent state into images. So we can see what the agent thinks might be imagines will be happening in image space. And you'll see that indeed, hopefully you can see, it's a bit blurry, that the agent imagines that it is like picking up and throwing the statue repeatedly. So in other words, it seems like the translation of the latent representations are correct. It's just that the agent's model itself about the world is wrong. And we think this could be an interesting future area of work, like, can the translation sort of capture why the agent's model about the world is wrong? But in practice, we haven't yet been able to disentangle at sort of test time translation errors from model errors. So if anyone has some thoughts on that, happy to chat after. And very finally, just to end on, this is sort of an example in the stochastic setting. We have some more results since then, but basically this is if you compute multiple plans from the same starting state and their translations, you will indeed sort of capture the true stochasticity of the environment. So very loosely speaking, in the results we've done since this, we find that like almost 50% of plans would say like flip a coin, it lands on heads, and 50% say I will land on tails. But instead of a coin flip, this is a navigation task through some random teleporters where the distribution's a bit more complex. But yeah, what the agent basically says it will do is indeed a reasonable reasonable approximation of what may actually happen. And yeah, I'll finish there. I'll leave on this summary slide. Thanks for listening, everyone, and would acknowledge my great lab led by Matteo, as well as funding agencies and stuff. But I'll flip back to this for questions. Thanks, everyone.